Hello and welcome to the webinar organized by Mainstreaming Innovation Project here at Glasgow Caledonian University. My name is Branka Dimitrijevic and I will moderate today's event. I'm also directing the project Mainstreaming Innovation, which is a joint project of 9 Scottish universities that provides support for collaboration between businesses and universities in developing and testing innovations for low-carbon infrastructure systems. This is a live event, so if there is a fire alarm or online interruption, please try to reconnect, but you will also be able to watch a video recording of this webinar in a few days. Presentations will finish around 1:30 and the webinar will close around 2 o'clock. You can start using chat facility to ask questions anytime during the webinar, but the answers will be provided after the presentations between 1:30 and 2 o'clock. Before we start with presentations, I would just like to say a few words about our project, Mainstreaming Innovation. We support innovations for integration of low-carbon infrastructures, and the scope of the project looks into, first of all, natural infrastructure, landscape and biodiversity as a resource, but also as an instrument for mitigation of climate change and adaptation to climate change. Directly connected to landscape, of course, is water, and we look into harvesting, saving, reuse, then waste, its reduction, reuse, and maybe to energy. Regarding energy issues, we look first of all into energy efficiency of buildings, innovations for achieving better energy efficiency, and then energy generation from renewables and low carbon transport, including electric vehicles, but also cycling and walking. And in the middle of this image, you see information communication technologies. The links between all these infrastructures indicate that we are looking for synergies, how they connect, what efficiencies can be made, how costs can be reduced if they are better connected. So that's in brief what our project is about. Today's webinar is about assessing future overheating risk in buildings, and the speakers are Professor Phil Banfill of Heriot-Watt University and Dr. David Jenkins of Urban Energy Research Group at the Institute for Building and Urban Design at Heriot-Watt University. Welcome, and I would kindly ask you to start with your presentations now. Thank you.
Okay, thank you very much, Branka, and we're very grateful to have the opportunity to present our work through the Mainstreaming Innovation activity. What I'd just like to start off by doing, this is going to be a bit of a double act. I'll start off and then hand over to my colleague Dave a little bit later on. So we are from, as Branka says, from the Heriot-Watt University School of the Built Environment. We are part of what the group we call the Urban Energy Research Group. The purpose of today's seminar is to tell you something about a research project which we've undertaken over the last few years, which has led us to a method of assessing overheating risk in buildings in future climates. What we'll aim to do is to tell you something about the background of the tool and then give you some examples of how it works. But before that, if I could just say a little something about the School of the Built Environment. There we go. So we're a School of the Built Environment. We have 3 research institutes covering infrastructure and environment, building and urban design, and housing and real estate. About 100 academics in total. But we also host a Royal Academy of Engineering Centre of Excellence in Sustainable Building Design, which is one of only 4 in the whole of the UK, and the only one in Scotland. All 3 institutes work together through that academy, and we are within the Urban Energy Research Group. A small part of that, we have about 20 people, variously researchers and research students, and within the group, it's that one. Okay, sorry about that. We're having a little senior moment here with the mouse. So within the Urban Energy Research Group, we have a number of themes dealing with, for instance, building performance simulation and modelling, which we'll talk a little bit more about later, low and zero carbon buildings, a bit of a focus on historic and traditional buildings, but some of the more social aspects like fuel poverty and behavioural change are there as well. And we've carried out projects on dwellings, offices, schools, factories, wind farms, energy networks and so on. And over the last approaching 10 years, we've had about £4 million worth of research funding. So the kind of research methods that we adopt, we do building performance modelling and simulation, energy monitoring and analysis and assessment, life cycle assessment, carbon accounting and the like. Integration of systems into buildings as part of retrofit activities, but we also have a focus on economic methods and, as I've hinted already, qualitative methods like interviews and surveys and behavioural research. The Low Carbon Futures project, which we're here to talk about today, is just one example of the research that we've been involved in, and this was a £700,000 research project that was funded by EPSRC through their adaptation and resilience to a changing climate programme. ARC for short. And ARC supervised a total of 18 projects across the UK. Not all of them were going at the same time, but there was a total portfolio, and there was a network which is still in existence for the few remaining projects, the 5 or so projects that are ongoing. And if you want to find a little bit more about that, there's a link there to the ARC network website. So the Low Carbon Futures project itself came from a kind of general research question, which was that the new generation of future climate predictions were to be based under development through the last 5 or 6 years, were to be based on probabilistic projections rather than deterministic. The difference being that you have a prediction which shows that there's a range of possible climates, a range of possible scenarios, rather than giving you a single figure, perhaps for temperature or humidity or something like that. So this adds a level of complexity, and the real question was, how can we use this in designing buildings and designing adaptations to buildings? What can we change about those building designs in order to enable them to perform satisfactorily in the future climate? So it was a matter of taking all that lot, all that complexity, and coming up with hopefully a method, a toolkit perhaps, which would be useful for industry who would be interested in predicting overheating and indeed undercooling perhaps, and the energy consumption and the carbon emissions associated with that in the future climates. So the project as a whole consisted of 3 main elements. First of all, we had building modelling, which is recognising that most buildings of any significance, any significant complexity, will be modelled using one or other of any of a number of building energy and performance simulation software. So there's a choice of packages that are out there in the marketplace, some open source software as well. And this is increasingly being used by the building design community, and we wanted to be able to give some examples of case studies as to how any proposed tool would fit together with the building modelling software, and give us an overheating assessment. So the number of different overheating assessments that have been offered in the literature, different criteria. One criterion, for example, that's widely quoted, and which you'll hear more about in the course of this webinar, is the proportion of occupied hours of your building at greater than 28 degrees centigrade. This is the SIBSE criterion, and the criterion that's adopted is more than 1% over 1% of occupied hours over 28 centigrade. Your building is then considered to be overheating. So that's one element, which of course also leads you to how can you adapt your building design to meet that overheating criterion, to deal with that overheating criterion. The second component was dealing with the complexity that's provided by the climate projections weather generator. UKCP09 has this wonderful weather generator feature to it, and it will give you a climate profile for an entire year according to different scenarios, future time slices and the like. So there is potentially an enormous amount of information, an enormous number of such climate profiles, climate files that's available, and this needed some statistical processing. So we undertook a statistically rigorous process to attempt to come up with a simplified way of looking at this complexity, so that we can then deal with the wide range, the variability of individual building performance outputs that would come from simulating each of those climates. So what you could imagine doing would be to feed each of those climates through the weather generator into a building simulation model. Huge task for a building designer to do. So what we wanted to try to do was to simplify that process statistically and rigorously. And the way we chose this, as Dave will explain in a moment, is that we came up with an emulator model, which, as I say, rigorously deals with the statistical complexity. And the third component, there we are. A third component, I suppose you could call this knowledge exchange. We worked with the design practitioner community to try and assess what their perceptions of climate change and the future are. We also looked at, worked with them to get their opinions as to what would be a useful format in which the projections could be cast. And this involved us with focus groups and online questionnaires and interview sessions, working with practitioners. And at the end of the exercise, once we'd produced the tool, we then got some feedback. We went back around the loop and got feedback from them as to how we might be able to cast the outputs in a format that would be useful to them. So overall then, you've got these three overlapping, intersecting components to the project, and just some numbers there, just to give you a feel for the amount of work that was carried out over the 4 years of the project. We did 26,000 dynamic building simulations on a number of different exemplar buildings. We processed 2,000 climate files, each of which have a large number of points. We're talking about tens of thousands of points in these climate files. And then we interacted with 84 different, let's call them individual feedback responses. So that is a very sort of high-level overview of the project, and now I'll hand over to Dave to take us through in a little bit more detail.
Thanks, Phil, and good afternoon. Before going into the background of the LCF tool and some of our main conclusions, it's probably useful to do a bit of background knowledge to look at the things that sort of motivates the research in the first place. So to start off with, it's also useful to distinguish between these two terms we use, mitigation and adaptation, because they do occasionally get confused and overlapped. When we refer to mitigation, certainly in the area of building modelling, we're looking at reducing the carbon emissions of a system, in our case a building, through some kind of change, so looking at reducing carbon emissions. Adaptation is more about changing that system to make it suitable for a future climate, particularly as we believe that a future climate will have a high probability of being warmer. Now, of course, there's some measures that can be both adaptive and mitigative. You make a change to external shading, for example, you reduce the overheating risk of that building, but you might also be reducing the carbon emissions because perhaps your air conditioning unit is going to be used less often. So they are linked, but it is sensible to distinguish between those two terms before we proceed. And when we talk about building failure, which is what we do on the Low Carbon Futures project, and ways that climate change can cause that building failure, there's of course many different ways that can happen. We're more concerned within our project on poor thermal comfort during warmer summers. So what's the temperature inside buildings going to be like in the coming decades? But of course there's other ways that climate change can cause problems within the built environment. Inadequate drainage during intense rainfall events, for example, if we've not got properly sized drainage systems attached to buildings. Flooding and rising water tables. If you're building, if you're looking to build on a floodplain, you might have sort of second thoughts if there's a high flood risk in that area. But you might also change the use of a building that's already in a high flood risk area. And then also slightly more indirectly, perhaps, is the transport and infrastructure links to that building. If they become jeopardized due to changes with climate, then you might have to rethink what you're using those buildings for. But we're particularly concerned with that first issue of thermal comfort during the summer. So adapting buildings for thermal comfort. When we're looking at overheating, we know, of course, that overheating can be caused from a variety of issues, and usually is a combination of things rather than a single factor. Certainly in non-residential buildings, offices and schools, internally generated heat from people, lighting and equipment, growing IT use, for example, that can have a huge impact on the overheating risk of a building. But of course we do have some control over that. We can make our computer equipment more efficient, our lighting more efficient, and think about the sort of occupancy densities of our spaces. But we then have external factors like climate that perhaps we have less control over. But we can look at combating those external factors by making changes to the building, like external shading, like changing the glazing to reflect more solar gains, and also improving ventilation strategies and so on. So there's various measures that we can apply to the actual building fabric or the heating, ventilation, cooling systems. And so we might refer to those as adaptations. And that's what we're looking for in this project. But if we want to identify if the building is failing due to overheating, obviously we have to define what overheating is, which is a non-trivial exercise for the built environment. Obviously different buildings have different definitions of overheating. In a dwelling we might be looking at high temperatures at night, stopping people from sleeping, and that might be the trigger that causes somebody to want to make a change in their building. Whereas in an office, you're there during the day, you might be looking at afternoon threshold temperatures that you don't want to exceed. Phil mentioned previously the 1% of hours above 28 degrees, which is used quite a lot. It's quite a crude definition, but it is used in our building design guides that we tend to use for overheating studies. But we shouldn't see thermal comfort as being completely prescriptive. People don't work in quite that way. We know people adapt to temperatures. We know that if there's higher temperatures outside the building, then people tend to cope with higher temperatures inside the building as well. So we wanted to, as we developed our method around the Low Carbon Futures project, we wanted to try and reflect this kind of more complex attitude to overheating. Mechanically cooled buildings is obviously a slightly different picture because providing your cooling plant is large enough, which it usually is, the building shouldn't overheat if the cooling system is working adequately. So perhaps we need to define a different type of failure for this type of building. And so for a future climate, okay, in extreme examples, we may have undersized cooling plants, which would be a problem because you can't get to your desired temperature inside the building. But there's also the case that your cooling plants might be large enough, but because you're dealing with a different cooling load profile due to changes around climate change, perhaps the operation of that plant is no longer optimum. You might have designed it to meet or to run at a certain part load if you have multiple chillers within your cooling plant. And of course, if you're then meeting a different shape of cooling load, that can have an effect on your overall efficiency of your unit. But perhaps a bit more obviously, I suppose, is the energy consumption and the CO2 emissions that you might associate with your cooling system. If the cooling load's going up, then your energy and CO2 emissions of that cooling unit is going up, likewise. And so you might want to put some kind of barrier on that. You might say, well, I don't want my energy consumption of my cooling system to go above this threshold, and so I'm going to make some kind of change to my building to ensure that doesn't happen. Of course, if you're doing a CO2 analysis of your building, you need to think about what's going on in the winter as well as the summer. So we'd want a tool that would be able to do that as well. But these are some of the issues that we might think about when we're looking at mechanically cooled buildings as opposed to naturally ventilated. So we're looking at applying climate information to our building models. So what does climate actually look like, first of all? Well, here's some historic data, which I'm sure many people are familiar with. Rising temperatures around the globe. This is from the Met Office, Hadley Centre. And then if we focus a little bit on the UK, we see a similar kind of trend. We see rising temperatures historically. And most of us are probably familiar with this type of data, but the question is then, how do we project that for future climates? Of course, we're very reliant on for example, Hadley models around climate projections, but the climate projections we use within buildings tend to be split between two types. There's the more traditional types, which we might call deterministic, and then there's the more recent projections that we've been using on the Low Carbon Futures project, which we might describe as probabilistic. So deterministic projections, anyone who's used the UK Climate Impact Programme 2002 or UK CIPO2 projections will be familiar with these. You might get a single value of climate projection with no associated probability of likelihood. So we may think of a certain region warming by 3 degrees within a certain timeline, within a climate scenario. And there's no probability, it's just a single value that we use to try and gauge the likely warming in that region. Probabilistic projections are slightly different in that we might have, for example, a 10% chance of that area increasing by 1 degree or less. We might have a 30% chance of that area increasing by 3 degrees or less. So you have a whole spectrum of possibilities with different probabilities assigned to all those different values, which makes it slightly more representative of the original climate models that we're using. But of course, it makes it a lot more complex. You have far more sort of data sets, far much more information that you somehow need to process through your building studies. And that's really part of the challenge of our project. Quite a nice way of comparing those two types of projections, the deterministic of UK CIPO2 with the probabilistic of UK CP09. This is from the UK CP briefing report, which you can access online with the link at the bottom of that slide. So UK CIPO2 might tell us that for a given scenario, whatever that might be, that there was a 5.5 degree increase in temperature being projected. So okay, you could use that in your building studies, and that's represented by the blue dot on that graph that you can see. The red curve represents what UK CP09 would say about that same scenario, where you might have, in this case, a 56% probability of a 5.5 degree warming or less on that cumulative frequency curve you can see in red. But there's all this other range of possible values with different probabilities assigned as well. So the question is well, do we actually want to get some of the kind of lower and higher probabilities through to our building assessments as well, rather than boil it all down to just one number? And so that's kind of the sort of ethos behind the probabilistic projections. So that red line is better representing the climate models than that blue dot. That's really the key. And some examples of UK CIPO2 projections. As I said, I won't go over this in too much detail, but you have, for these monthly values, in this case of average air temperature and monthly rainfall projections, you have single values for all these months. So useful values, but they are single, they're not probabilistic, they're deterministic. And then we switch to UK CP09, and we see it's a bit more complicated. So you see those maps at the bottom of the slide. We have perhaps a 10% probability of that amount of warming or less. We have a 50% probability of that amount of warming or less, and so on. So we need to think of clever ways to incorporate that type of information into our building models. And there's much more on the UKCP website for those interested in UKCP09. And because of the complexity of that information, we need some kind of conduit of getting hold of that information. And we use something called the weather generator, which is available on the UKCP website. And other projects within the ARC consortium also use this weather generator. So here we have projections given for different percentiles of probabilities in a way that I've already described. And then there's also algorithms within that interpolate from monthly down to daily, down to hourly values that we can use with building modelling, because we need that hourly resolution to run our dynamic building software, which I'll come to in a bit. So the weather generator sort of looks something like that. You put in your emission scenarios, so low, medium or high greenhouse gas emission scenarios. You have your time periods, a baseline time period, along with some future time periods. Usually there's 7 future time slices that you can access through the weather generator. And then you choose your location. The weather generator then churns up all that information and produces ultimately hundreds, even thousands of possible climate files. And when I refer to climate files, I mean the kind of climate file you use in a building simulation package. So an hourly description of all the climate metrics that you need to run a building model. So UK CIP02 might give you 1 climate file. Through UK CP09, we end up with hundreds, possibly thousands of climate files. So that's an issue, clearly. And for those of you familiar with running building simulation packages, this graph is just to represent what an hourly temperature profile looks like for an entire year from a building simulation package. So you might have 3 different versions of your building, for example. You might have a no adaptation case, and then you might have 2 adaptation technologies that you've applied to your building, and you want to compare the temperature profiles across the 2. Now, if you did that for just 1 climate, you'd have 26,000 data points. Quite a lot, but pretty much manageable for most people with, even just with the Microsoft Excel, you can manage that. But then if you have 100 climates describing each 100 climate files describing each climate scenario, and you might want to run lots of different climate scenarios, then you get to the point where it's too much information. You have millions of data points. Never mind the fact you have to collate all that information, but you have to generate it in the first place. So the calculation procedure takes just far too long to put that through dynamic building software. So our solution is something we call model emulation. So we're trying to emulate these complex dynamic building software packages. So we do, first of all, we choose 100 climates to describe a future climate scenario. So as I say again, 100 climate files, hourly climate files, just to describe the spectrum of different probabilities, different possibilities that you get from that particular individual scenario. We then simplify that climate data through a process that we call principal component analysis. I won't go into the details of that, but essentially what we're trying to do is boil down this huge amount of climate information into the main variables that we think are important for predicting, for example, internal temperatures within a building simulation. And it's important to remember, of course, that if you're trying to predict hourly temperatures and you want to know, for example, the temperature at 2 o'clock in a building, then you need to know the climate information not just at 2 o'clock, but also 1 o'clock, 12 o'clock, 11 o'clock, 10 o'clock, and all the previous hours, because of the thermal response of a building, the time lag of a building is quite important in this type of dynamic calculation. So you can end up with a large number of input variables, which is why we use this statistical process, PCA, to boil down those variables into a smaller number of variables. And by doing that, we can then look at those climate variables going into the model. We can look at the building simulation outputs, so input and output. We can then develop a regression relationship between that input and output on an hourly level. And that means that if we then want to throw in another climate file into that calculation, we don't have to go back into the dynamic building simulation. We can actually use that regression relationship, which is a far more efficient, far quicker calculation than running a full simulation. And that's really the key, the sort of foundation to the LCF tool. Of course, that abbreviates the calculation procedure. It makes it a lot quicker, a lot more efficient, but you're still left with the equivalent of hundreds or even thousands of building simulation files. So we still need a way of presenting that output. And so quite a large part of the project was really about, well, we've got all this information which describes, in effect, a probabilistic analysis of how that building was responding to climate. But we need to do something with that information so that someone can actually use it. Otherwise, it's a fairly academic exercise. So that's something that we concentrated on, and I'll draw on some of the outputs that we've produced later on. Of course, we also want to integrate it with existing design methods. We want to make this easy on the building designer. We want, within a commercial environment, of course, there's time constraints, resource constraints. So we want something that just is an appendix to an existing procedure that's carried out, so it can actually be used commercially. So if you imagine you're a building designer running this LCF tool, step 1 would be that you carry out an hourly dynamic simulation. So for those of you who've run building simulation software like IES or ESPR or TAS, that type of simulation that you might do, or you would hope that you would do anyway for a building, and you'd run that just for a single climate file, whatever that climate file might be. And what the LCF tool then does is it looks at the climate information you've used, it looks at the results of the building simulation that you've just run. It develops a relationship, as I say, through this regression method between the input and output. And then that regression relationship is fixed for that building. And it means you can come along with any climate information whether it's from UK CP09 or elsewhere, and just run hundreds or even thousands of climates through your building by accessing the actual regression tool, not by accessing the dynamic building software. So you've run your single simulation. The tool's done its clever bit on it sort of automatically. You then provide a little bit more information to our LCF tool, just to sort of fine-tune the regression relationship around things like times of occupancy, definitions of failure. You can put in any definition of failure that you wish, providing it's based around hourly temperatures or hourly cooling loads. Choose your required assessment, and this kind of information takes less than a minute to put into the tool. We do have plans of maybe integrating the tool with an existing software package, in which case you wouldn't even need to put this information in because it's already there inside your building model. And step 3 is really just to click go, just to run the tool and let it do its thing. So within the tool we have already 10 climate scenarios, a baseline climate scenario, and then 9 future climate scenarios based around 2030s, 2050s, 2080s, and then these 3 emission scenarios as well on top of that. So that amounts to 9 future climate scenarios. And as I say, within each future climate scenario, there's 100 climate files. So that's a total of 1,000 climate files that are within the tool. And as soon as you click go, the tool will run those 1,000 climate files through your building model, which will take a fraction of the time to running 1,000 climate files through a full dynamic building package. So we have these hourly results for all the scenarios stored as text files, but of course you probably don't want to play about with 1,000 text files from building simulation. So we then have graphical output that boils down this information into something more usable. And just a couple of notes on the tool. Although we set it up for this overheating analysis, which is based around hourly temperatures, we do find it works equally successfully for cooling and heat and load analysis. And we have published several validation papers comparing the results of our tool with the results of lots and lots of full building simulations, and we get quite a good correlation. But this raises the possibility of perhaps a probabilistic energy analysis of the building, because if you can predict heating and cooling loads, then you can predict the energy consumption of that building in a probabilistic way as well. And this is something we're thinking about currently. Phil mentioned the practitioner feedback part of the work, so this is quite a key area of the project. We ran a series of focus groups, surveys, questionnaires, interviews, to try and get a feel of what industry thought of the process that we were carrying out, whether they thought it was useful, what kind of output they'd like to see. But we also ran a final focus group in September just to sort of disseminate the final work, but also kind of clarify whether the outputs that we'd come up with were correct, were useful and usable. So as part of that exercise, we presented 2 main forms of output that we can get from the tool, and just tried to get a bit of feedback on whether we'd chosen the right output. So the more complex sort of outputs that we produced from the tool is this probabilistic graph. I won't go into the detail of how it's actually constructed, because that would take quite a long time. But the important thing to note is, first of all, along that x-axis we have our definition of failure. So in this case, it's percentage of occupied hours above 28 degrees. We use that magic 1% value that we spoke about earlier, and that's represented by that vertical dotted black line. So what we're looking at is, for our different climate scenarios, how many files within each climate scenario exceed that threshold. So if we look at the y-axis, this is the probability that failure is going to occur according to our models. If we look at the blue curve, that represents the current climate, we have a failure predicted of about 6%. So according to our models, there's a 6% chance that particular building will exceed the failure threshold. So that's very low. We might think, okay, our building is fine for a current climate. We then look what happens to the red, green, and purple lines, which represent our 3 chosen future climate scenarios for this case, and we're up into the 80-90% risk categories. So if we believe our models, if we trust our models, then this is telling us we need to do something to that building if we want it to still be comfortable in the next 20, 30, 40 years. So we applied some adaptations to that building, and we can see, I'll go into specific adaptations in a second for our case studies, but we can see in that case there's a substantial drop in the overheating risk for this, or the failure risk for this building. Even for 2050, we might suggest that that building is reasonably low risk. We're at about sort of 20-odd% chance of failing, based on the criteria we've applied. 2080, we still have a fairly high risk, but then perhaps the designer or the designer's client might start to question whether they actually need to think about 2080 as a timeline. Some clients might be interested in that timeline. Some of the feedback we've had is that actually 2080 is probably too far ahead for many, certainly retrofit projects, but even some new builds. 2080 isn't really the priority, but the tool does give you that option if you wanted to demonstrate that. So straight away, the designer has some options to decide what to do to that building. But of course, you present this to a client, and perhaps they don't get the full sort of impact of what the model is doing. It's not necessarily appropriate to a client. So the second type of output that we that we generated, we call this risk matrix. So what you have here, along the bottom of that table on the left, you have 4 different adaptation options. You have no adaptation, first of all, so the building as it is. And then you have 3 future adaptation options, which are whatever you might have defined using whatever choices. And then along the vertical titles, you have the 9 different future climate scenarios. And then you have a percentage chance of failure that we've gauged. So this is the percentage chance that your building is going to exceed your definition of failure. So we can see for the current climate, for this particular building, there was no risk. So okay, that's fine. The building's been built as it should have. It's not designed to overheat currently. But we can see straight away, you jump to 2030, and there's quite a high overheating risk. So what you can then do is you go along, if you like the x-axis, you go along to the right of that table, and you say, right, well, adaptation 1 has reduced that risk substantially, but it's still maybe too high for comfort. So you go along to AD2, and you find that actually that adaptation has taken your building back down to a low overheating risk level. And of course, if you have cost metrics applied to those adaptations, if you've done a proper capital cost analysis of those technologies, then you can start to do this risk against cost benefit analysis. So is it worth, for example, jumping from AD2 to AD3, where you can see actually the difference in overheating risk is relatively small. So if there was a high cost associated with AD3, both the designer and the client might decide it's actually not worth spending that money. But there's quite a big difference in the overheating risk between AD1 and AD2. So you might decide that even if that was quite an expensive measure, you might decide it's still worth doing that because it offsets some of the overheating that we're imagining might happen due to a warmer climate. And in our report, which I'll reference at the end, we sort of encapsulate all this information into little summary sheets for all our case study buildings. So on the left, you might not be able to read this, but if you look at the report, you'll see these fact sheets at the end. On the left, we just have a description of the building and the inputs that are going into that building. And then on the right, we have all the outputs that we produce from the LCF tool that we think can guide the designer into making the correct decisions in relation to what might happen to that building in a future climate. And just to very quickly finish off, these are the case studies that we used that are presented in the report. If we go over, so there's 4 main case studies and several adaptation options within each case study. I'll just very quickly go through some of these results using this overheating risk matrix, or this failure risk matrix. So let's say we had a detached house. This one was based in London. And we might choose a failure definition of 1% of occupied hours above 28 degrees. We also carried out this exercise using a bedroom temperature risk threshold as well. And you get slightly different results. So let's say we had no adaptation and we see the building isn't failing in the current climate, but then we go forward to 2030 and certainly 2050 and 2080, the overheating risk becomes very, very high. So you need to do something to that building if you want it to function in the future. At least that's what our models tell us. So just by improving the window opening strategy at night, and also by putting in external shading, and even to a certain extent reducing the appliances and lighting, we find that certainly by 2030 we can reduce that risk to a very low level. You may argue that the window opening schedule might already be applied to your baseline, but it would be up to the designer how to place that, whether they put it into the baseline or whether they use it as a specific adaptation. Reducing appliances and lighting tend to only have small effects on overheating for residential buildings. We find, as I'll show you in a second, as you go into non-domestic buildings, it becomes a lot more important. So we've partly solved that problem through our adaptations according to our risk matrix. If we then go to another case study, which is a primary school in Edinburgh, maybe slightly surprisingly, it already has a high overheating risk in the current climate. And there have been stories of schools overheating even in Scotland in the past few years in the summer for a variety of reasons. We're using a slightly different failure threshold here. It's from Building Bulletin 101, which says that we shouldn't exceed 120 hours of occupied hours being over 28 degrees. And in this case, to try and reduce the overheating risk, we carried out some natural ventilation strategies, again external shading, and particularly important for this building was reducing the appliances and lighting. So making sure, first of all, you switch things off so that they're not constantly heating the building when there's nobody there. But also using efficient computers, efficient lighting, just really drilling down those internal heat gains as much as possible. We worked on a project called Tarbase a few years ago, which did a kind of bottom-up analysis of the energy consumption and heat gains from equipment and lighting, and so we've applied those assumptions to this project. Again, this is all detailed in the project report. Then mechanically cooled office. Our failure in this case is that we don't want the cooling load of our future scenario being greater than the maximum predicted in the current climate. So, as I said, there's 100 climates within each climate scenario. So we take the climate in our current scenario, the baseline scenario, we take the one that gives the greatest cooling load, and we define that as our threshold. That's the thing we don't want to exceed for our future climate scenarios. So perhaps unsurprisingly, the building has a high excess cooling risk in this case. But applying fairly similar measures, but specified and designed in different ways, so external shading and really reducing the appliance and lighting by quite a large amount. The baseline building in this case was quite a high internal heat gain building because of the amount of high density of computers. And again, we make quite a dramatic change, and most of that change is due to the reduced appliances and lighting in that particular case. We don't want to overgeneralize these results because you put in a different building and you'll get a different set of results. So we are clear that this is relevant to the case study, relevant to buildings that are similar to the case study, but we don't want to overgeneralize across the entire stock. And just finally, we also worked on a project called Calibre. This is led by Loughborough University, using a house that was being built to 1930s standards in Nottingham University. So we were on board that project doing a bit of building modelling for them. The interesting thing about this project is that they then carried out low carbon retrofit measures to that building, and they looked at energy consumption, both modelled and monitored. So we can see, because it's a 1930s building, the probability that, according to our models, the probability that building is going to overheat both now and in the future is very, very low, which you'd expect from quite a drafty, poorly insulated building. But what we want to use this tool for is, these retrofits are not designed from a point of view of adaptation, they're designed from a point of view of mitigation. But we wanted to carry out an adaptation assessment of those low carbon retrofits. And what we found was that, the first improved retrofit, as it's labelled, so a low carbon refurb, lots of insulation, a reasonable amount of draft proofing. If you go to the Calibre website, you'll get the details of all the different technologies that were applied. We found actually that the overheating risk was pretty much the same after that improved retrofit. It was actually slightly lower than expected. And this isn't always the case, particularly in non-residential buildings. If you make them more airtight and put in lots of insulation, you do have the possibility that you might be increasing the overheating risk. It wasn't the case in this building, according to our LCF tool. When they then carried out a further retrofit exercise, so they really knocked down that airtightness through further draft proofing, so it became a very airtight house, and they then installed mechanical ventilation heat recovery into that building. Then the overheating risk went down even further, perhaps because there was this reliable ventilation during the summer, because this system was left on throughout the year. So our model suggests that actually the overheating risk would go down even further in this case, but it already started off at quite a low level anyway. So what we're doing here is we're ensuring that our low carbon retrofits are adaptive. We're ensuring that even in a future climate, all this money you're spending on your low carbon retrofit shouldn't be detrimental to your building from an overheating point of view. So just to finish off, to sort of follow on from that point, adaptations should be building specific. Just like our case studies are not overly generalized, they're specific to that building. Each building might have a specific concern that you design your adaptation to address. And so our software needs to be sensitive to that fact. And the fact that it relies on dynamic building simulation is an advantage in that respect. And the concept of adaptation, just as with that Calibre project, should be applied to all low-carbon refurbishments. There's pointless spending thousands, even tens of thousands of pounds on refurbishing a house and then finding in 10, 20, 30 years it's not really working particularly well. It's also important to remember that buildings overheat for a variety of reasons. We shouldn't think just because we live in a cold climate, for example in Scotland, where we're based, just because it's generally not that hot outside. There's lots of reasons why a given building might be overheating, particularly in the non-domestic sector. And when we throw future climate into that mix, we might be exacerbating a problem that already exists. So when we design any change to that building, we should be sensitive to what the future climate is projected to be. But we still need to make sure that buildings are already working in the current climate. We're designing for this future climate, but in many cases, our buildings are maybe not performing as they should be in the current climate, which can affect our sort of approach to refurbishment. And the UK CPO9, so UK Climate Projections 2009, they are quite complex, they are quite, they do take time to manage, but they can be used with appropriate building software, providing they've been appropriately sort of tidied up through statistical processing. And we find this actually quite useful to translate this term probability into risk. So you're using this probabilistic climate information to carry out an overheating risk analysis. And then it becomes more aligned with maybe other types of risk analyses that a building designer might carry out on a building design. And suitable output can inform choices at building level for adaptation measures. And we spent, as I say, a lot of time on this. It's more of this is in our report. So we can design for reduced future overheating risk and create something that's usable within a building project timescale. We were very keen for this not to be just an academic exercise. We wanted to have something that actually talks to the people who want to use this tool. And hopefully we've gone some way to succeeding on that score. And just finally, for those interested in the project, this final project report is now available online. And if you have any questions, obviously please contact us. We're also on Twitter if you have some interesting questions around this project or any of our sister projects to this work. And that's us. Thank you.
Thank you very much. Well, it is now time for questions and answers. We are still waiting for some questions from our online viewers. But let's start with discussion about what you have done and how this tool can be used. Is the tool ready to be used by the industry? Do you think it's...
Yeah, I mean, our kind of next stage of development would be around the interface of the tool. So we have this calculation engine that we've validated, and we feel we've tested that quite rigorously. So we're looking at ways of applying an interface so that it's more user friendly. But the time taken to run the calculation, the way the output's generated, I think we've got that in a sort of time scale that's usable in buildings. It's just really getting the sort of commercial side of it finalised, and deciding whether we want to align this with an existing building simulation package or we want this as a standalone tool. I mean, there's different ways of applying it, but the calculation engine, the assumptions behind that calculation engine, even the equations behind that calculation engine, it's all now out there in the public domain. So we're just looking at the most appropriate way of applying this now, really. That's the next step.
I think it's also worth mentioning that it's not, as a tool, it's not tied to any particular simulation software. It's blind to the particular simulation package that you might be using. So at the moment, it could be used with somebody used by somebody using whether it's IES or Ecotect or TAS or any of these other packages.
How much time would be required how much time should we add, let's say, to the design of a house or an office to be able to use this tool and check all these possibilities, future options?
I mean, if you wanted to use the default 100 climate scenarios, then you'd be talking about a couple of hours extra time on a design project. Obviously, if we were to develop the interface, we would look to get that down even further. the thing to remember is it's not replacing an additional task that a building designer might carry out necessarily. It's providing a new analysis. So it will involve more time, but I think we've kind of got it down to a point now where the time it's almost a drop in the ocean compared to the total timescale of a building project, the design stage.
And it can all be done on desktop computers. It doesn't need any fancy computing facilities. It's crunching the data is okay on the sort of desktop computer that most people would have in their offices.
And in fact, we didn't have a complicated computer cluster to run these. We were quite keen to keep it as a desktop study. So our tens of thousands of building simulations that we ran to validate the model, that was all on sort of desktop. We run the tool itself just on a very bog standard desktop. To ensure that it is actually, it doesn't require a huge amount of processing power to run.
A more general question: how useful are climate change projections? What do you say?
They're useful. The point is all these projections tend to rely on the same climate models. It's translating the information that's coming from those climate models. And I think the feedback that we've had is that there's plenty of designers out there that want to use adequate and appropriate climate projections, but sometimes you might present them with this sort of probabilistic format, and it looks like a lot of work. So that's why you need this kind of sort of halfway process that takes the scary data from the climate projections and translates them even further to a level that's actually usable. And once you get down to that level, I think most designers, or certainly a large proportion of designers, look at that information and say, right, that is now something I can use. Whereas if you just point them to the weather generator, for example, that's probably not particularly useful or particularly usable for many people in the industry.
A question from Doug McNabb: what climate change scenario should we use, and what probability?
That's a very good question. The probability level, I guess, would be something that would either be developed. If we wanted adaptation to be a serious part of building regulations, then we may sort of decide a probability threshold that we might use. But at the moment, you might sort of discuss probability and risk level with a client, and you might decide, right, well, that level is acceptable for my building design. In terms of the first half of that question, in terms of what climate change scenario you should use, that's more difficult to answer. What we try to do with the LCF tool is we try to include, as I say, the nine different scenarios, and then you can make a judgment out of that. And so you may decide, right, well, the high emission scenario for 2080 is still indicating that my building is going to fail. But you can make a judgment that if all the other scenarios show that your building isn't going to fail, then perhaps you would go ahead with the advice that the tool is providing. Whether we get to a stage where, as part of a almost due diligence process within a building design, the designer has to show that for a given climate change scenario, for a given emission scenario, for a given timescale, that building is still going to function in the way that they hope it does. Whether we get to that stage, I don't know. It depends how seriously we take this type of adaptation in building design. So it's a good question. I wouldn't say the project has come to a firm answer as to you use this climate scenario to judge your building.
I think there's something else that could be added about the level of probability, because I think this is something where we need to have a lot of interaction among the design community and the user community, because you think of structural design. Probabilistic structural design has developed over probably a century. Certainly all the time I've been in the built environment, so back to the sort of 1970s, risk probability of failure criteria for structural elements and the like were just becoming mainstream in CP 110 for reinforced concrete in 1972, for example. So that's taken sort of 40 years of maturity since that point, and the discussion, the debate, if you want to call it like that, hasn't really got started yet. So I think there's plenty of people out there who have something to say about what would be an acceptable risk probability, risk criterion. Clearly, it's not life-threatening in the sense that if a structure collapses, people will be killed, but in a different way. We have situations like happened in 2003 when a large number of people died through overheating. Older people died through overheating in that very hot summer then, and that kind of focused people's minds. So I think there's a policy and human sciences debate that needs to be taken as to what actually could be an acceptable risk level to set for well, I mean, I was implying in all this, I'm implying the risk of overheating. But going sort of back to the question, which was about the probability levels of climate changes, what is going to be acceptable? And we just don't know yet because we haven't had that enough of that discussion.
Yeah, I think it is, to sort of repeat the point really, adaptation is a fairly new concept in the way that we're applying it. 10 years ago, for those who use SIBSE guides and similar kind of design guides, you wouldn't have had such a detailed discussion of adaptation. You certainly wouldn't have had a detailed discussion of probabilistic climate projections. In fact, the latest SIBSE guides that are coming out are now using these probabilistic climate projections, but they're only just using them. It's new. It's a new thing that we're applying to our building assessments. So both the probabilistic climate projections are new, and this concept of adaptation is fairly new in the way that we're talking about it today. So of course, it will take time before we actually pin that down as to what we want to do with it.
Regarding the feedback that you had in conversations with building users, building clients, what would you highlight as the most interesting insights or contributions to your research, or has anything influenced your thinking or modifying the tool, or what were the reactions to the concept of the tool or its applicability?
Yeah, I think all the feedback was interesting. I mean, what was clear was that because we had quite a broad range of building professionals within our feedback exercises, there was a broad range of opinions. I mean, there are people who are just not interested in this type of climate projection at all, which is fine. People have other priorities. So that was the first interesting thing, was that there is this broad view. But within that broad view, there are people who generally want this information. They understand how important this is, and they want something that they can use. But they can't go off and spend an extra, they can't double the amount of time they spend on a building project because they won't get paid for it, because the client won't be prepared to double their fees. So it was really around understanding that there's almost sort of two types of output that you want this tool to produce. There's the sort of academic rigorous output that you want to have something to fall back on, but you want to have something that's usable in a sort of almost intuitive sense, so that the client understands why the client of the building project understands why they might get some benefit from it, and also it's something that can be just produced very quickly and efficiently. So it's sort of taking yourself out of that academic environment and putting it into the environment where this tool is hopefully going to get used.
We have a question from Ian Biggin of Phase Energy. When will the tool be available for use in its user-friendly form?
There's no, I don't want to shirk the question, but there's no simple answer to that. I mean, we are looking at, like any sort of academics, researchers in our position, we are looking for funding to extend the next phase of the work. We can use it as a consultancy tool right now. If someone came to us with a building simulation model, we could run their building through our tool as a consultancy tool. But of course, we're then using the tool ourselves. What we would like ultimately is for other people to be able to use the tool. I can't put a timeline on that currently, but we do have things sort of in the pipeline that we're hoping to get extra funding in, so we can make that available. But the tool is workable right now. If someone presented to us a building simulation result with a climate file that it used, and we can run through those steps that I went through in the slides. So that's something that we could do right now.
It's essentially a resource and commercialisation issue rather than a technical issue.
Okay. A question from Ivor Macaulay of Glasgow Housing Association. Can you see the potential that the outcomes from the model and varying probabilities could be used well in a BIM as BIM becomes more prevalent?
Yeah, possibly. I mean, there's quite a lot of interesting stuff going on at the moment, linking BIM with building energy performance models. I think we'd want to sort of pin down precisely how the tool works with dynamic building simulation first of all. I think you know, to sort of put the cart and the horse the right way around, I think we'd want to look at ways of integrating dynamic building simulation into BIM and vice versa. And I know there's progress made with that in the last couple of years. And then we would sort of start to think about how our LCF tool, which is an appendix to the dynamic building simulation part of that model, how that would then integrate. So I think there is potential there, but yeah, it's getting the first stage through first. So we want to integrate our model with the dynamic building simulation, and then if the dynamic building simulation can integrate with BIM, then all the better.
A question from Linda Forbes of Scribbly Consultancy. A post-occupancy evaluation study suggests buildings do not perform as well as their rating suggests. How or is this taken into account in adaptation calculations?
Well, our adaptation calculations are based on building models, and yeah, I mean, you're absolutely right. I mean, we know that building models do miss. You compare building model results with real energy data, and you can be looking at a difference of 2-3-fold. So there is, because our tool is based on building simulation, then obviously if there is a weakness, then it's the weakness of building simulation. So I guess if you don't trust building simulation models, you won't trust our tool. So the question is how you use simulation appropriately to adequately describe what's going on in a real building. And that's partly up to the building modeler, partly down to the software. But yeah, I mean, I completely agree. I mean, it is a big problem, this performance gap, and we need to really start to think of intelligent ways of recalibrating the core building models, the building software itself. But I mean, our LCF tool, the regression relationship it carries out, it can be performed on any type of software. So if you upgraded if as we improve building simulation software to better reflect real energy performance data, then our tool, likewise, the regression relationship would be improved. But we are sort of reliant on the success of the building simulation in the first place.
A question from Colin Reed. Could this modeling technique be adapted, and do you intend to simulate the heat island effect external to a building, but within a relatively enclosed space, for example, tight urban streets?
It's possible. I mean, providing there is a strong relationship between the climate information and that system, then yes, that regression relationship could be developed. This isn't something we thought of. We tend to be more concerned with what's going on inside the building. It's quite an interesting idea. As long as there is a strong regression relationship, there's no reason why you couldn't repeat the process, except your system is now, as he says, an urban street as opposed to a building. You can kind of exactly the same principal component analysis approach, the regression approach, again looking at input and output, and yeah, I mean, I think it's unlikely we would do that because that's not quite our field. But I'd be interested if somebody else wanted to repeat what we've done and apply that method to a different scenario. That would be quite interesting, certainly.
Certainly worth mentioning that one of the other projects within the ARC network, I think it was Scorchio was the acronym, was explicitly concerned with the urban heat island effect, and that was based, it was the group in UMIST in Manchester that were used. So have a look on the ARC network website to follow that one up.
And urban heat island is obviously of huge importance, but you have to be a little bit careful when you're using your climate source. Is actually picking up the urban heat island? So is your London climate file actually picking up the effect of the urban heat island in the first place? Because you don't want to put on an urban heat island correction factor to a set of climate information that already has the urban heat island sort of integrated within it if it's based on real weather station data. So there is a sort of a slight fly in the ointment when you're doing that process. But provided you understand the data, then yes, there's no reason why we couldn't, or someone couldn't try carrying that out.
Mm-hmm. You mentioned in your presentation and comments about how clients perceive these projections until 2080 as maybe not relevant for them. Do you think that there are buildings, for example, public buildings, let's say museums, hospitals, that will stay there, should stay for a long time, and maybe in some of them, like museums, for special collections, you need stable environment and you need it for a long time. Would that be a good reason to plan for 2080
Yeah,
and ensure that you have stability of environment, indoor environment for?
I think for many buildings there is a strong argument for doing that. But I think you then have to sort of come back into the reality, and as I say, the feedback we get from some building designers is that they can just about see the justification for doing 2050 in some cases, certainly 2030, maybe 2050. But a lot of feedback was, I mean, we can't suggest paying money to upgrade our sort of housing association stock or our office building on the basis of how it might perform in 2080. And of course, I do have some sympathy to that view, because we're relying on building models, we're relying on climate models, we're then projecting this forward 60 years, 70 years, then the margin for error is already quite high as you go further and further out into the future. So if you're then trying to suggest spending tens of thousands of pounds on a change to a building on the basis of that projection, then I would be sympathetic to someone who says not so keen on doing that. But there are some buildings, of course, that you might want to, particularly new build projects that are currently in the pipeline, it might be easier to justify going forward to the sort of 2080 timeline.
Thank you very much. We don't have any more questions unless someone asks while we are still discussing. But do you have some final messages, or what about plans? You mentioned a little bit about your further research in this area. Anything else to add to that, or how you see the development of the next stage?
I mean, I think there's quite a lot of work. I mean, the way we use building, particularly dynamic building simulation, the way we use that now is quite different to 5-10 years ago even. And there's a lot more potential for doing quite interesting things as processing power improves, our access to data improves, and so there's lots of areas where I think we can use building simulation in quite novel ways. So that's an area that we're looking at. In terms of the tool itself, as I say, we're keen to apply this to more real building projects. We're keen eventually to not just have it as an in-house consultancy tool, but to have it as something that other people can use. And if anyone has any suggestions for collaborations and they want to sort of engage with these ideas, then obviously we're always interested in talking to people in that respect. And I mentioned the probabilistic energy analysis. So although we're looking at overheating and so on, so you can put a risk on a certain thermal comfort level that might be in a building, we'd also like to develop the tools so you can start to do a similar type of analysis around energy and carbon emissions. So you have probabilistic energy outputs. So what's the percentage? What's the probability that the building's energy consumption will exceed this amount? So you can almost start to think about what's the probability of a building exceeding the building regulation target for carbon emissions, for example. You might model it as meeting that target for a current climate, but by 2030, 2050, it's exceeded that, or it has a certain percentage chance of exceeding that target. So you might use that to justify more work on the building as you're building it. So there's lots of sort of potential avenues from the LCF tool that we hope to have a few spin-off projects from.
And I think the questioner who mentioned BIM and linking with BIM software, clearly there's a huge agenda around building information modelling, and as the years roll by, more and more sophisticated ways of integrating systems, information systems, will come through, and I think there's a clear possibility for integrating these kinds of probabilistic performance issues, perhaps as against benchmarks in energy management systems. If we roll the BIM is currently perceived as being a design and construction and handover tool, but it's not beyond any big step it's not a big step of further development to have an extension to the continuing management over the lifetime of the building, and particularly with public-private partnerships where risk is taken by the building owner, the building operator, and they will be dependent upon these management software processes. So I think there's potential for further linkage and further development there.
Thank you very much. Phil and David, we don't have any more questions. I would like to thank you for your presentations and to thank to our online viewers for questions. But before we close our webinar, I would like to attract attention of our online viewers, and especially of those who live in Scotland, that we are planning a live event on 9th of December at the University of Edinburgh, and we are inviting innovative businesses to present to and network with researchers in low carbon infrastructure systems. We already have 3 innovative businesses who will be presenting, one about refurbishment to passive house level, refurbishment of housing. The second one will talk about hydrogen generator that he is trying to improve and apply in practice. And the third business will talk about wastewater purification. We are inviting other businesses to contact us if they wish to present to academics at this or any future live events. Please book places online at our website, and thank you very much for watching this webinar. Thank you.